Hello and welcome to the Math Studio. In this video, we're going to use an alternative method to solve trigonometric equations. Now, in a previous video, we looked at this particular example, this particular trigonometric equation, which is solve 3 cos x plus 2 sin x equals 1 for x between 0 degrees and 360 degrees inclusive, using t formulae. But there is an alternative method that we can use, which is called the auxiliary angle method. So I've already written out the proof, but just to sort of speed the video up a little bit. So I'm just going to explain that for you. So let's have a look and see how this works. So the way it works and the theory is that we can replace the left-hand side of the original equation. So it's this 3 cos x plus 2 sin x with a trigonometric ratio of a compound angle. So we're going to replace 3 cos x plus 2 sin x with this expression, a sine of x plus theta. And theta is what we call the auxiliary angle. So we need to find a value for A and a value for theta such that this expression here is equivalent to this expression here, 3 cos x plus 2 sin x. So let's go to the left-hand side here. So this is A sine x plus theta. Let's expand that and we get A sine x cos theta plus A sine theta cos x. And that's equivalent to 3 cos x plus 2 sin x. Now, I've rearranged a few things here. So the a sine theta cos x, I've moved that to here. So to make that our first term instead of being the second term. And a sine x cos theta, I've moved that to become the second term. And I've also transposed or switched around the cos theta and the sin x as well. So see how you've got sin x cos theta here. It's now become cos theta sin x. Now, because it's a product, the good thing about multiplication, of course, you can just switch things around and it doesn't change the value, which is great. And that's equivalent to 3 cos x plus 2 sin x. Now, what I've underlined here is very important. So now we're going to equate terms. So let's have a look at the left-hand side. This term here that involves a cos x is equivalent to this term here on the right-hand side that involves cos x as well. That means that a sine theta must be equal to 3. That also means that a cos theta must be equal to 2, since the two expressions are identical, they're equivalent. So this gives rise then to two very important equations. We have a sine theta is equal to 3, and I've written that there and we've called that equation 1. We also have a cos theta is equal to 2, and let's call that equation number 2. So now our mission is to find a value for a and to find a value for theta. So let's find the a first. So finding a. What we're going to do, we need to eliminate somehow the sine theta and the cos theta, and the most convenient way to do that is to square both equations and add them together so that you end up with a sine squared and a cos squared, and we can eliminate that using a Pythagorean identity. So squaring both equations, we have a squared sine squared theta plus a squared cos squared theta, so that's both left-hand sides, is equal to 3 squared plus 2 squared. So that's the two values on the right-hand side. So we end up with a squared outside of sine squared theta plus cos squared theta equals 13. Now, sine squared theta plus cos squared theta is equal to 1, of course. So a squared times 1 is just a squared. So we have a squared is equal to 13. Therefore, a is equal to the square root of 13. So I'll just put a little sort of asterisk there. We need that value. Now we need to find the theta. And the way we do that is we go back to our equations 1 and 2, and we can divide 1 by 2. That will eliminate the a's, that'll cancel those out, and then you end up with a single trig ratio. We end up with the tan ratio because we're dividing sine by cos. So again, if you just divide one equation by the other, is equal to 3 on 2, and that sort of becomes tan theta on the left-hand side is equal to 3 over 2, and therefore theta is equal to inverse tan 3 over 2. So I'm going to leave it in exact form. I'm not going to evaluate this angle or this theta. This is the value of our auxiliary angle. Right, now let's substitute the value of a, so that's sort of another very important value. We're going to substitute our value of a and our value of theta into this compound, this trigonometric ratio of a compound angle, the a sine x plus theta. So what we end up with is 3 cos x plus 2 sin x is equivalent to the square root of 13 times sine of x plus inverse tan 3 on 2 is equal to 1. So we're only focusing on this equation here. We're not worrying about the 3 cos x plus 2 sin x, since we've converted it into a different form. So we end up with, let me just move the page up a bit. We end up with sine x plus inverse tan 3 on 2 is equal to 1 on root 13. Now that's a positive ratio. That's sine of some angle is equal to 1 on square root of 13. That's positive, which means that we need to consider quadrant 1 and quadrant 2, or the angle could be in either quadrant 1 or 2. Now when I say the angle, I mean x plus inverse tan of 3 on 2 is either in quadrant 1 or quadrant 2. So now we have our two cases. So case 1, and I've sort of labelled it as equation number 3, is x plus inverse tan 3 on 2 is equal to inverse sine 1 on square root of 13. And our case number 2 is, and I called it equation 4, is x plus inverse tan of 3 on 2 is equal to 180 minus inverse sine of 1 on root 13. So this is quadrant 1, this is quadrant 2. So now solving each of those two cases, okay, so you end up with, okay, so from number 3, okay, so equation 3, rearranging the equation so we have x as the subject of the formula, we end up with inverse sine of 1 on root 13 minus inverse tan of 3 on 2. Now we have to add 360 to it, and the reason for that is, in fact, I'll just demonstrate this quickly. You'll end up with a negative angle, so I'll just show you what happens here. So I've kind of missed a step here, so just for the purposes of speeding up the explanation, but I just want to make sure that I explain this particular point. Minus inverse tan of 3 on 2. Now that's going to give you a negative angle, and you'll end up with negative 40 degrees or thereabouts, or negative 40 degrees in 12 minutes. So in order to turn a negative angle into a positive angle, we can rotate the ray 360 degrees. So imagining there's a ray from the origin drawn sort of in quadrant 4. It's still a quadrant 4 angle, but if we add 360 to it, it turns it into a positive angle, and that's within our original domain. So always remember that we need to express x as a value between 0 and 360 degrees, so no negative angles allowed. Okay, and so we end up with 319 degrees, 48 minutes. Now the other case is the quadrant 2 case, so x is equal to 180 degrees minus inverse sine of 1 on root 13 minus inverse tan of 3 on 2, and you get x equals 107 degrees and 35 minutes. So just writing the answers on a separate line, therefore, x equals 107 degrees 35 minutes, or 319 degrees 48 minutes. Now I've checked both of those, but just to show you quickly, and I think this is also just being prudent, check both answers. Okay, so I'll just demonstrate one of them here. So if we check 107 degrees 35 minutes, what we could do is store it in a memory location, shift store, and let's store it into the letter x, or the pronumeral x, and we'll just type it out. So 3 cos of x plus 2 sine of x. Hopefully we'll get a value pretty close to 1, and I think that's pretty close. So that's equal to the right hand side there of 1 in our original equation. And of course you can check the other one. You're going to get a value that's pretty close to 1, and you can check me if you like. And that's it. Thank you very much for watching.